Alright, I'm back. Well, I spent the break trying to salvage the recording from the first half of the class, but I failed miserably. So we don't have a recording for the first half, but mostly I went over stuff that's on Canvas, so hopefully no big harm done there. But my recording software sometimes gets a little strange. So, alright, so I didn't dig up a chip, but let's see. But we'll go without it anyway. Alright, so let's take a look at the data sheet. So this chip, it's an 18-pin chip. It looks like, you know, a 7404, which is a 14-pin chip. It's the same size, it's just got 4 extra pins. It runs off of 5 volts. It's got power and ground on pins 14 and 5. And the pins are described by this picture, and the first thing to notice is that most of these pins have multiple definitions. For example, pin 1 is labeled RA0/AN0. This pin can do 2 different things. RA0 is what we call a digital pin, AN0 is what we call an analog pin. So we can use this pin to read and write digital values, high or low, or we can read analog values, a voltage between 0 and 5 volts. Pin 6 is got 3 different purposes. RA2 is a digital pin, AN2 is an analog pin, VREF- is something different. It's a reference voltage that we can use for something called analog to digital conversion. Okay. This pin 12, this has 6 different purposes. RB6, PGC, T1OSO, T13CKI, P1C, and KBI2. Okay, most of these pins are multi-purpose. And we're going to work with some of these, and some of them, especially the ones related to clocks and oscillators, we're not going to worry about too much. But as we go through the course, we'll expose more and more aspects of this system, and we'll learn what more and more of these different pin behaviors are about. The next thing to note is that, you know, we typically work with the 18-pin version. There's also a 20-pin version. It looks exactly like the 8-pin, it's just slightly longer. It has 1 extra pin on each side. But the pin numbering is obviously different, because they go up to 20 instead of 18. But if you have more pins, then you have less multi-use for each pin, right? So we may have a pin with different purposes on the 20-pin package versus the 18-pin package. There's also a 28-pin package, and that's not a chip that looks like what we used in 250 that you can pop into a proto board. This is called a quad flat pack. It's very thin, it's got pins on all 4 sides. Not all of these pins are used, some of them are labeled no connection, but it's a different form factor. And in particular, it's very thin, so if you were to put this on a board, it wouldn't take up a lot of height. And that's useful when you're putting something inside a system. It cuts down on the dimensions. It's also physically smaller. It's not nearly the surface area of the 18 or 20 pin package. Alright, so we'll skip over the feature list, but I want to talk about this block diagram. This is everything basically that goes on inside this PIC chip. And we will know about most of these things by the end of the course. But here's the first part we're going to work with, what we can call the data path. There's a memory, okay, which has program information in it. These are the instructions, and again, there's 4,000 bytes worth of that in our chip, the 1220. And there's also data memory. So a RAM is a random access memory. This is the stuff that's being manipulated by the code you write. So there's actually 1 memory here and 1 memory here, and the rest of the stuff is kind of like the CPU. And it can do things like, say, give me a piece of data from this memory at a particular location, a particular address. and take the data at that location and do something with it, right? Use that to decide what kind of arithmetic operation we should do, or to do a multiplication of two numbers. And we can read values from this data memory, and we can write values into this data memory. And so this figure that we started with memory, CPU, I/O, right? So here's the I/O part. This is all the stuff on the outside world, and these are the pins that we saw in that earlier figure, RA0, AN0, RA2, AN2, VREF minus. Okay, these are the pins, and pretty much anything moving along this bus, this collection of signals, that's what a bus is, can be sent to or taken from these different input-output locations. All right, so we talked about registers in Engineering 250. So we start with a flip-flop, which can hold a bit. If we make a collection of flip-flops, we can make what's called a register, and this could hold, you know, several bits. Well, if we take a collection of these, we can put it together into something called a memory. And a memory is really just a collection of registers. So here's an 8-bit register, here's an 8-bit register, here's an 8-bit register. And the way we use a memory is we have something called an address, which we put into this memory, and then we have data, which comes out. So it's an addressable collection of registers. And typically, you know, the first register would be address 0, the next would be address 1, 2, 3, 4, 5, 6, 7. And so this is a memory that contains 8 registers. Each register is 8 bits. And if I want to read the contents of this register, what do? I put in an address of 5. And now what comes out of my data are the bits stored at register 5. And if I want to read the bits stored up here, I change my address to 1. And now what comes out of my data lines is the contents of register 1. So a memory is just a collection of registers, which each is a collection of flip-flops. And I can specify which register I want to read by putting a value into an address on this memory. And then the value coming out on the data lines is the contents of that register. And oftentimes memories are readable and writable, so we might have a separate signal called read/write bar. And the idea is if I put a 1 into this pin, the memory is doing what I just described. It lets me read the contents of a register. But if I were to put a 0 into here, that says I want to write the memory. And now it will read what's on this data bus and load that into one of these registers. Which register? The one specified by the address. So to the outside world, our memory looks something like this. We have an address. We have a read-write signal. And we have a bidirectional data signal. And if I'm writing memory, it reads the contents of this data bus, loads it into something in the memory. If I'm reading from the memory, I'll take the register indicated by this address and copy its contents to this data bus. Now we could build one of these with what we know from Engineering 250. It's a purely combinational circuit other than each flip-flop. And it's using multiplexers and demultiplexers and latches and things like that. But we're just going to think of this as a block, okay, called a memory. And that's what this block up here is, okay? It's called a RAM, a random access memory. And it takes in an address down here, and it doesn't show a read-write line, but there is a read-write line available. And here's the data bus, which can either go into the data latch or come out of the data latch and go somewhere else. And the same with program memory. It has an address latch, it has a data latch. A couple of things to think about, and we'll talk a lot more about this down the road. For the data memory, our address is 12 bits. So when you see something on a data sheet in angle brackets, like angle bracket 12, it means this is a 12-bit number. 12-bit data address. So we have register 0, register 1, register 2, register 4095. That's the biggest we can get with 12 bits. And the data that's stored in this is 8 bits wide. So this is basically a 4096 by 8 bank of memory. Except most of the locations in here don't exist. There's actually only 256 locations in here that can store information. But it's thought of as being a 12-bit address. The program memory contains 4,000 bytes, 4,096 bytes. The address is 21 bits, and the data coming out is 16 bits. So it's a roughly 2 million by 16 memory, but most of that space doesn't exist. There's only 4,000 bytes in here. Now if you look at the data sheet for a different PIC processor, you'll see totally different configurations of the memories. Okay, and we'll work with this a lot, and we'll start to see why the memory is set up like that, and what the ramifications of that are. All right, so memory, CPU, all of this stuff, and then input-output. Now this stuff is also part of the CPU, but it's actually more like other input-output stuff. These are things that would typically be located outside the CPU memory and would be attached, on a motherboard, for example. But they're all built into this chip. And these are things that let us request that things happen after certain time intervals. We can say after 2.5 milliseconds, I want you to do such and such. This is something that lets us communicate with outside devices like keyboards and mice. So the enhanced universal synchronous asynchronous receiver transmitter, the EU SART, is a way we can do what's called serial communication. So we can connect two of these PIC processors together and have them talk to each other using this subsystem. Eeprom is an electrically erasable programmable read-only memory. You talked about proms in 250 when you looked at configurable memory. Well, this is a prom, right? Remember proms, you have fuses that you can blow to program the device. This is an erasable prom, and it's electrically erasable, so we can program the fuses to store information in this prom, but we can also erase that programming and change it. And we can do that all under program control. This is a system for taking an analog signal, something typically between 0 and 5 volts, and turning it into a digital value. We'll have a lab where we play with that. And there's other subsystems as well. Alright, so detailed description of the pins, don't worry about this for now. But if you're curious, right, that's what all those pins do. Discussion of the different types of oscillators. So most of us, we have CPUs, they run at, a couple of gigahertz, 2.5, maybe 3 if we've got a really fancy machine, maybe more than 3 if we're overclocking, we've got good cooling. But a few gigahertz is pretty typical for most PCs that you would find today. Our PIC processor runs at 32 kilohertz. Okay, 32,000 ticks per second, not 3 billion, 32,000. That's pretty slow, but it's fast enough, right? 32,000 times a second. Well, how quickly can we see things, right? 30 frames per second, 60 frames per second looks pretty smooth to us. We don't really notice the flicker from one scene to the next if it happens in a 60th of a second. So 60 things per second is almost faster than our eye can notice. 32,000 per second, that's actually quite a bit. We can do a lot in 32,000 clock ticks. I'll close that window if it gets really loud. We can do a lot in 32,000 clock ticks per second. Certainly the kinds of things we're going to be doing in this course where we're, responding to switches, turning lights on and off and so on, this is going to look more or less instantaneous to us. Okay, unless we deliberately make things take a long time. And that's a built-in clock. Okay, there's also a built-in 8 megahertz clock. If we really want to go fast, right, we can do 8 million ticks per second, but we'll generally do 32K. And this is, that clock that's going into the state machine from 250, so we can change state that many times per second. So a whole bunch of information about that. This is a figure we'll come back to a lot, but this is basically our 8 megahertz clock. Inside, this is our 31 kilohertz clock. And we'll come back to this figure and see exactly what all this stuff means. But just for sales pitch here, there's a multiplexer, right? Remember what multiplexers do? They take multiple inputs, they choose one to go to an output. Well, here's a classic application of a multiplexer. We have 8 different clocks, all the way from 8 megahertz down to 1/8 of a megahertz, and then this special 31K. And we can choose which of those clocks, right? Each of these are ticking on and off at their own frequency. We can choose which of those we want to send to this line. And we do it by using these 3 select pins on this multiplexer. And if we set these select lines to 111, we have an 8 megahertz clock on this line. If we set them to 000, we have a 31 kilohertz signal on this line. And before that signal gets sent to the peripherals, it can be selected from one of 4 sources. Something called a phase lock loop, these external signals, or that internal clock. And we have 2 bits here that we can use to choose which of these 4 things we want to send down here. And then if we have this switch closed, that's the clock that gets sent to the CPU. So lots of multiplexers inside these things. Alright, we're going to see lots of figures like this, because there's lots of registers in this system that have very particular meaning. Okay, and they're generally 8-bit registers, and so we'll see a picture like this showing 8 bits. We'll see a name for each of these bits, and these names are significant. We can use these names in code. We'll see a description of them. We'll have an indicator above saying whether it's read-write or read-write, and also what its default value is. So idle n is a read-write bit, and it normally has a value of 0. And if we look at bit 7, idle n, bit 0 means run mode enabled. CPU core is clocked in run modes. If we look at bits 6, 5, and 4, which is IRCF 2, 1, and 0, they're all read-write, and the default value for each is 0. If we have 0, 0, 0, what does that mean? We have a 31 kilohertz clock. These 3 bits, which are in, this register, which is in the data memory, those 3 bits, IRCF 210, those are the bits that are used to control which of these signals gets sent into our CPU. Alright, so we'll spend a lot of time going through this data sheet looking at different sections. I will post after class this datasheet quick guide, which, as I said, is about 18 pages. And I recommend keeping a copy of this nearby, downloaded, if you like, print it out, because this is most of the stuff we'll be referring to. Pinout, basic block diagram, and then the individual instructions, description of what the instructions do, something called special function registers, and so on. There's the special function registers. But none of that is too concerning to us for Lab 1. Okay, for Lab 1, we don't really need to know what our code is doing, or even what the PIC processor is doing. Lab 1 is really a kind of getting our feet wet. So let me talk you through Lab 1, and I'd like you to start working on Lab 1 once we're done with lecture, around 2 o'clock. We may run a little over today. But let's take a look at the first lab. There's a lot of detail in here, and it's possible there are some things that are incorrect, but it's been written pretty carefully, and Izad and I have looked at it and gone through it, and we believe this is pretty accurate. But it's possible that the first time you do this, you'll have some different environment and so on. So this should get you there, but you know, if something seems strange, go ahead and ask. All right. So objective of this lab, basically getting used to the development environment, something called MP Lab. It's actually called MP Lab X. And it's just the software that we're going to use to write code, to check the syntax on code, to simulate code. Okay. So first step, you need version 5.1 of this software. It's very important you use version 5.1, not the latest version. Okay, so let's click through on this. And Windows, Mac, or Linux, this should work fine. So come down and find version 5.1 and download it. And it's the usual installation drill. So do whichever one works for you. And let's go through some experiments. Okay, so I've already downloaded this. Let me go ahead and start MP Lab. And this is more or less what it'll look like for you. I don't have any projects. I've got this start page up here in the front and just a bunch of empty space. Okay, the start page is you know, kind of a introduction to stuff, and you can buy things and so on and so forth. I'm just going to close that out. Okay, I'm not really going to need that. And let's go through the steps here and talk a little bit about what's happening. So basically, this is the environment in which you're going to start a project, add a file to it, write code for that file, check the syntax of your code, do what's called assemble it, okay, turn it into ones and zeros, and then for us, simulate it. And a quick kind of refresher, I think you've done this in 121, and we've definitely done it in 224 and such. We normally work in these high-level languages like C or C++ or things like that, and we do what's called compile these things into effectively assembly code. So this is something .c, this is something .asm, or maybe .s. And then this goes through something called an assembler into machine code. There's a lot of other steps in here, but this is a first order view. This is the human readable stuff. If x is bigger than 5, then y equals z plus 2. Right? So this is the high level language. A CPU doesn't know what to do with if x equals 5, then z equals c plus 2. Right? So we have to change this into something that the CPU, the hardware, can actually understand. And that's usually done through an intermediate step. We compile our C code into what's called assembly language. And assembly language is still human readable, but it's a much lower level. It's a version of our original program that's very close to what the machine can work with. And then the assembler turns that into basically binary. And that binary is what gets loaded into the program memory of whatever CPU you're on and then executed. Okay? We, in this course, we're skipping this. We're starting directly at the assembly language level. So we're going to write assembly language code. We're going to assemble it into ones and zeros. And instead of running it on a piece of physical hardware, we're going to run it through a simulator which acts the way a physical piece of hardware would work. So this is the environment, this integrated development environment, IDE, that we're going to use to do all of those steps. Okay, so experiment 1 is basically getting you used to that. So step 1, create a project. Start MPLAB, I've already done that. Go to the menu and say File, New Project. Okay, every time that you do something in MPLAB, you probably want it to be a new project. Okay, experiment 1 will be its own project. Experiment 2 will be a different project. I don't know what this does. I want to write some test code to see if I understand such and such. That's a new project. Okay, this is one of the most important things I can tell you. Don't mix things together into a single project, because it will confuse you and it will frustrate you and it will cost you time. Okay, everything you're going to do, make it a new project. You can always copy and paste if you've got a piece of code you want to reuse, but it's really hard once you've got things glommed together to split them apart. So I'm going to say File, New Project. Okay, and these instructions are in the lab. First thing, you're just going to go on and say Next, because we're doing a microchip embedded standalone project. Those are the defaults. Just go ahead and say Next. Next thing, you have to choose which device you want. You have all of these options. They all kind of look the same. So the easiest way to do this is to go in here and just type, let me go back. Just go in here and just type pick 18F1220. Okay, you can find it in the drop-down menu, but there's probably thousands of them to go through. So pick 18F1220, that's the device we're using. That's super critical. If you use just about any other device, your code's not going to work the way you want. So put in your device name, say Next. Okay, next step, simulator. Okay, if we were in the lab, we would use a PickKit 3, and it's a physical thing we can use to program chips. We're just going to use a simulator. So click Simulator, say Next. Okay, tool chain. We're not going to use C in this course. We're going to use assembly language, and we're using something called MPASM. So click on that, say Next. And now you put in your project name. Now, the first time you do this, pick a good location for your projects. Pick a directory that's empty, that's in part of your regular backup schedule, right? And that makes sense for you. Okay, so I've got mine under Summer 2020 projects under 270, but put somewhere that makes sense. I don't recommend just putting it on your desktop. Okay, take the 15 seconds and make yourself a folder somewhere. Okay, and then put in your project name. So I'm just going to call this Lab 1 Experiment 1. I recommend not having spaces in there. I've got a space in here. It's going to yell at me about it forever, but if you don't want to get yelled at, don't put spaces in there. Okay, and then just say Finish. Okay, I've got a bunch of stuff now. If I come down to my folder here, there's my Lab 1 Experiment 1.x. I've got all this stuff under here. I've got a debug and a default, and I've got an end project with all these files and private and so on. Don't monkey with any of that. Okay, your best bet if you're doing MPLAB is only do things from MPLAB. Be really careful going into that directory and doing anything yourself. Okay, because if you confuse MPLAB, it will refuse to play with you. So let it do all the manipulations. All right, so we've gone through all of these steps. Okay, next step, add a source file. You're going to do this every time that you do this. You're going to make a project and then you're going to add a source file. Okay, so I'm going to right-click on my experiment. I'm going to say New. And what I want to do is assemblyfile.asm, but the first time you do this, you may not see that option. So if you don't see assemblyfile.asm, click on Other, and come down to Assembler, and there you'll see assemblyfile.asm, and say Next. Okay, now you're going to put in the file name. You can call this anything you want. Okay, I'm just going to call it main, because it's a main program. And now I've got a main.asm sitting over here. And I've got a tabbed browser over here, and there's a tab called main.asm, and here's where I can write my code. So I can type in here. All right, so we've added a source file, we gave it our name. Step 3, so like some of the labs in 250, we're giving you pieces of this, okay? So in this case, we're giving you all the code you need for this experiment, right? Because we have not talked about what any of these things mean, but this is assembly language. Okay, we'll be spending the next few weeks going into detail about what each of these funny-looking mnemonics means. Move WF, add con 1, tris B, 0x01, XOR F. We're going to learn about all of these things. Okay, but for now, we're just going to copy and paste. So this will give you a different experience depending on your operating system and your tools and so on. But I'm just going to select all this stuff with the mouse. Right-click copy, and then I'm going to come back into here. I'm going to click over here, and I'm just going to Control V to paste. And it's going to paste it in a way that works for me. But it may be that when you do this, everything gets shoved over to the left, and it's all left justified. And that might cause you some problems. So I'll give you a hint. If I select a bunch of text and I hit a tab, it'll move everything I've selected over. And if I hit a shift tab, it'll move everything I've selected to the left. So if everything is shoved over to the left, you're going to need most of it to be moved in. Okay, so you'll be doing this in lab. You can ask questions as you go through it. But anyway, here's the program that I've just typed in that I basically copied from the lab. Okay, copy the following code into main.asm, saving using the menu file save. So you can come over to File and Save, and you can also just do Control S, which is what I usually do. And anytime you make a change, right, this tab will be bold-faced saying you haven't saved this yet. If I hit a Control S to save it, now it's not bolded, so I know I've saved my latest change. So it's kind of the usual IDE experience. All right, and there's a note here. All instructions must be indented. Labels and defines must start in column 1. So loop colon, include colon, those need to start in column 1. These number sign defines need to start in column 1. But the other stuff needs to be indented. Okay, if I don't indent that, I'll get a problem when I try to compile or try to assemble. All right. So paste all of that in. Let's assemble the project. So production, build main project to assemble the code. So production, build main project. And if there's anything wrong in here, I'll see a message in red or blue. If the message comes out in green and says build successful, I'm good to go. Okay, you can also build by hitting the little hammer. Okay, that's the build main project. Now suppose I have a typo. Suppose I actually typed this in and I had a typo and I try to build this. I don't get my green success message. I get a red message saying build failed. Okay, what you want to do is scroll up to the first message that you saw. Okay, here's a warning. Found a label after column 1. Here's an error. Illegal character 0, and this is pointing to line 26. If I just click on that, that'll take me to line 26. Alright, I gotta close the window. There's nothing outside my window but pavement. It's a parking lot. I don't know what they're landscaping. That's okay. So find the first message, not the last, right? And click on it. It'll take you to where there's an error, and it's like, oh yeah, I had some extra characters in there. Okay. If my code did not get indented, right, and I try to build it, build successful, but I did get a warning. Okay, found an opcode in column 1. I can click on that, and that's telling me this line should have been indented. Okay, so I can just put a space in there to indent it. Alright, so that can take some messing around with, and this stuff is you know, bizarre looking. If you've never done assembly language, it's barely what you would call human readable, but it actually is, right? All of these things will make perfectly good sense to you after a couple of weeks. But for now, we don't have to worry about what they do. Okay, it's a bunch of code. It's going to get changed into ones and zeros, and then the simulator is going to execute it. Okay, so production build main project. Make sure that that you have a build successful appearing at the bottom. Anything in red or blue you have to look at. All right, let's take a look at what happened when we built this. So window debugging output disassembly listing file, and there's a detail in here. Okay, so window debugging output disassembly listing file, and I get this message: unable to generate the disassembly listing file. Please make sure you have built the project with symbol information. Open project properties, select loading under conf, and check load symbols. Okay, that's described in here. And you have to do this once per project. So how do I do this? I'm going to right click on my project. I'm going to say set configuration. I'm going to say customize. I'm going to come down to loading. I'm going to check this box that says load symbols. I'm going to say OK. And now I'm going to rebuild my project. And suddenly I've got a cool window out here with a bunch of stuff in it. All right. Here's my main program, my source code, my assembly language. When I say build it, what it does is it changes all of this into a bunch of ones and zeros. Here are the ones and zeros it changed it into. They're written in hex, okay, but hex is just a representation of binary information. So a lot of this stuff is stuff that doesn't actually generate code. It tells the system what you want to do. For example, I want to use a PIC 18F1220. I want numbers that I write to be interpreted as hexadecimal. I want to use this symbol port A to mean 0 hex F80 and so on. But here's an instruction clear F port A that got changed into the hex number 6A80. Here's an instruction clear F port B that got changed into the hex number 6A81. Okay, 6A80 in hex looks like this in binary. It's 16 bits. That's an instruction. That is the machine language equivalent of this assembly language instruction. So we write this because we know what clear F and port A means, and this software translates it into these 16 bits, which the PIC chip or the simulator understands. Okay, so this is this assembly step. This is assembly code, this is machine code. And what we have here is a list of the results of that assembly. Here's all of the instructions that we wrote, the assembly language. Here's a slightly different version of them, and here's the ones and zeros that they got translated into. And what is this first set of 4 hex digits? That's the address in memory where this instruction is stored. And these instructions are stored sequentially starting at address 0. So if I were to load this into a PIC chip or into a simulator, at instruction location 0, I would find the bit pattern 6A80. At address 2, I would find 6A81. At address 4, I would find 0E7F, and so on. So this is the actual ones and zeros. This is the lowest level of the hardware. This is the stuff that gets ingested by that whole state machine that we were looking at in that block diagram. And this is provided for us when we have a project and we say build it. It will create this listing, this disassembly listing, that shows us what our program got turned into. And this is one of the pieces you want to include in your lab, is this disassembly listing. Okay, we'll talk about that.
Does it count by twos?
It counts by twos because this is 2 bytes, and the addresses are inherently byte-oriented. So location 0 is actually the 80, location 1 is the 6A. And then this is locations 2 and 3, 4 and 5. That's a really pertinent question that we'll come back to a few times. But that's the first order answer. All right, so we've assembled our code. We've seen a disassembly listing. We have the ones and zeros. We're ready to do our simulation. Okay, so series of steps for this. And again, this is in the write-up, but let me just go through this. So first thing you want to do is set what's called a breakpoint. The simulator is going to execute the steps that the CPU would execute if it was given this program. And if I just run this program, we don't know what it's going to do, right? What we really want to do is ask the simulator to step through this program one instruction at a time, so that as it runs, we can examine what's happening to different spots in memory. So we want to step through the code one step at a time. So to do that, once our simulation starts, we need it to stop and wait for instructions from us. So we're going to set what's called a breakpoint. And to set a breakpoint, basically choose which line you want to break at, come over here into this column where the line numbers are, and just left click. And you'll see a red square and your line will turn red. That means there's a breakpoint there. And if I don't want that breakpoint, I can click again to make it go away. And you can set breakpoints anywhere that you want. Okay, but for this experiment, just set a breakpoint at that clear F port A. All right. So next we want to look at the values of some locations in memory. We want to look at 3 locations, something called port A, something called port B, and something called WReg. So we're going to go to debug new watch. And I'm going to type in port A and say OK. And I get this window down here which tells me port A is being watched. I'm going to click here and say port B. And I'm going to double click here and say WReg. Alright, I've got 3 variables that are being watched. Alright, so repeat the step for port B and WReg. So now I can look at locations in memory as the program is running. The other thing I want to do is I want to set inputs to this program. I want to pretend that I'm connecting 5 volts or 0 volts to one of these pins. In particular, I want to use pin RA0. So this is what's called a stimulus. So I'm going to go to Windows Simulator Stimulus, and I'm going to set up a stimulus for pin RA0. Okay, so Window Simulator Stimulus, and I'm going to click on pin and I'm going to type RA0, and when I hit this little arrow, that's going to do what we call firing the stimulus. Now right now it's set to say when I fire this, RA0 should be set high. I'm going to change this to toggle. Toggle means change back and forth between 1 and 0. So the first time I hit this arrow, my RA0 will change value. The next time I hit the arrow, it'll change value again, and so on. So I can keep changing it by hitting this arrow. Okay. This is doing what we would do in the lab if we had a switch hooked up to here and if we had LEDs hooked up to these ports and so on. It's letting us look at this in a controlled environment. Okay, now we go to debug, debug main project. So debug, debug main project, and I can also do this by hitting this button right here, which says debug main project. Okay, I run this and it says launching, initializing, here's your program running, here's your program stop. Breakpoint hit at line 23, And you can see my green line is right here where I set the breakpoint. Okay, the simulated CPU is running my code, and it's gotten to line 23, and now it's paused. And if I click on my variables window, I can see the values of my 3 variables. So port A, port B, and WReg, the value of each of those is 0. The address we don't have to worry about, but that tells me where these things are stored in the memory of the computer. Those are never going to change. The type is special function register. We don't have to worry about that. All we're really interested in is the value. And these are all 0 right now. Okay, so in addition to special function registers, you can watch general function registers, such as location 80. Okay, so we can click on variables and we can choose locations that we want. So we can watch locations 80, 81, 82, and 83. So I'm just clicking in here, and I'm putting these in hex, 0x82, and 0x83. And these are locations that I'm using in my program, but I'm calling location 80 count, I'm calling location 81 last in, input, and temp. Again, we don't really need to know what these are doing. We're just going through the procedure right now. Okay, so now we want to start stepping our simulation one instruction at a time. And there's a few ways to do this. We can say debug step into, which will move now to this next instruction. We can also use F7. We can also press this button right here. Okay, they all do the same thing. So it's just executed these 2 instructions. It's about to execute this instruction, move LW 0x7F. Okay, it always shows you the instruction that's about to be run. So if I click this button, it will run that one instruction, move LW 0x7F, and watch what's going to happen. Well, that wasn't very exciting. Oh yes, it was. So the value of this W register changed. And you know it changed because it highlights it in red. And WReg is equal to 0x7F. Well, that's exactly what this instruction that we just executed says. It says take 0x7F, load that into W. The next instruction says move WF, add con1. That's not going to show us anything, and WReg turned black again because it hasn't changed now. So it only turns red when it changes. But now we're about to say move LW 0x00. What do you think that's going to do? If move LW 7F set W to 7F, what's move LW 0 going to do?
Set W to 0, 0.
Set W to 0, 0. Let's find out. Hit that. Yep, WReg now changed to 0, 0. So we're starting to get an idea what this move LW is about. It takes a value and it copies it into this thing called WReg. Let's step this once more. And now we're about to move LW 0x01, and yep, WReg is 0x01. You can also see WReg up here. This little window up here always shows you the value of W. So it's 0x01. All right. So this should keep running until you get to a line labeled increment L. Okay. Oh, okay. Go to the stimulus window. So let's just step through this a whole bunch. So let's keep clicking through. and you can see what's happening, right? It's looping. If you happen to hit the run button, it will just keep running. It won't update these things while it's running, but I can hit the pause button and go back to single stepping. So it's in a loop right now, and it looks like it's just looping forever. Okay, so let's go to stimulus and let's fire this RA0. So I'll click that and it says stimulus toggle RA0 fired. And let's go back to our variables and let's step a few more times. And this time, instead of looping, it's going to go somewhere else. It's going to jump down here to this new section of code. So this code is written so that when RA0 toggles, it jumps down to this new section called increment L. And if we step through this 3 times, right, our W register changed, but this next instruction, our count value will change 0x80. And now that's going to change the value of port B, and port B is a 1. And now we go back to looping. And if I go to the stimulus and I fire this button again, and I step, guess what? Now port B is equal to 2. And if I fire that stimulus again and I run some more code, port B will increment to 3. All right, so that's the whole experiment, okay, and it's a 1 experiment lab. It's basically just taking this code that we've given to you, loading it in, and then going through these steps. But what you're doing in these steps is you're debugging a piece of software, right? So the goal of this software is to loop until RA0 changes value, and then add 1 to what the value is on port B. And we can see that that's exactly what happens. If I fire this pin, and then I start running some more, right, port B will eventually change from a 2 to a 3. Alright, and then you can debug, finish debugger session to end the simulation. Or you can just hit the stop button. Alright, so that's your lab 1. Okay, basically going through those steps. There's a lot of steps, right? Downloading the software, installing it, and then going through all the process of creating a project, putting in the source code, getting it to assemble correctly, setting up the watches and the stimulus, single-stepping it, observing what it's doing, firing the stimulus, seeing how it changes, and so on. Alright, so you want to perform all of that, and then you want to record your observations. Okay, so in your lab report, describe what you did, and you don't necessarily need to go into all of this detail, okay? But you know, you should say that you downloaded and installed MPLab. You don't need to say in there that I downloaded it from this location and so on, but you know, you downloaded and installed MPLab version 5.1. You ran it, you created a new project called such and such, you started a main file called such and such, you put in the following code, list the code that you put in, right, and put a note on here saying this is taken from, you know, Engineering 270 Online Lab version 1C. And then we set a breakpoint at this line and set up watches on these variables, set up a stimulus on this pin, stepped it, and you know, what did it do? Well, it stepped through a bunch of code and some variables changed, and then it got into a loop, and it sat in that loop forever and nothing changed. And then I hit the stimulus pin, and then after, you know, X number of steps, it started doing something different. and then port B changed to a 1, and then it went back into its loop, right? And experiment with it. Experiment with some of the other options, right? I can run this, and I could set a breakpoint down here. And now every time I run, it will stop when it gets to a breakpoint. So right now my program is running. I got the Cylon eyeball down there. If I fire this pin, it tells me debugger halted and it's sitting at this location. And my port B has changed to a 1. And if I run again, it goes back to running. And when I get to the stimulus and I fire this, it stops again at that location. And my output, port B, is now a 2. I can drag windows, so I can put my stimulus window up here, and my variables down here. And now I can go ahead and stimulate it here while looking at my variables, and my port B is a 3. And I can continue, and now my port B is a 4. So play around with this, right? This is the software you're going to be using for the next 8 weeks. The better you understand this, the more comfortable you are with it, the more success you're going to have. Okay? And just, break it. Make things go away, make things big, move things around, and figure out how to undo it. And, get yourself in all kinds of trouble. And you can come down to Window, and you can say Reset Windows, and get back into your original state. Right? But mess around with it. Okay? Clear problem statement in your own words. What are you planning to do in here for experiment 1? Answer to any specific questions. I don't think there are any in there. Pseudocode, there's no pseudocode for this because you're not writing the code yourself. But disassembled code available after successful assembling. Okay? So window debugging output disassembly listing file. That's the code you want to put into your report. Okay? And I'd like you to spend some time playing with this. So window debugging output disassembly listing. You want to put this in your report. Okay. So let's open up a word processor. So here's my report. If I Control A and copy this and then paste it into here, right, I get this. This is not terribly pretty to look at, right? Nothing is lined up, whereas over here, everything was like nicely lined up and organized. That's not the case over here. Well, why is that? Well, because most text processing we use what's called a proportional font, where the letter I takes less space than the letter X. But that makes it really hard to line things up. So this uses a fixed space font. So I can select all of this and I can try to find a fixed space font. For me, Deja Vu Sans Mono is going to work well. But, Courier is a classic fixed font and so on and so forth. And I might make this a little smaller. I might make it 10 point. And this looks pretty good. If I were to print this out in landscape mode, it would look even better because these lines wouldn't wrap, right? I could make this pretty small. I can go down to an 8 point, probably without getting into too much trouble with my teacher. And now, most of the stuff takes one line per instruction, and this is pretty straightforward to read. And a few of these longer lines got wrapped, but that's okay, right? So think about this. Think about how do you want to present this. And if you have one page in your report that's the disassembly listing and it's sideways, that's probably okay. I mean, I'm okay with that. If you want to do it in landscape mode, I wouldn't go too much smaller than 8 point. 7's probably readable, but experiment, right? And Word in particular tends to have an annoying habit when you paste stuff that sometimes it double spaces it. because there's a return at the end of each one that thinks each line is a new paragraph, right? Try to get rid of that. Right, select your text and format the page and adjust the paragraphing. All right. So include your disassembly listing. Test plan which describes input value and expected output memory values for a successful design. That doesn't apply here because you're just following a set of steps that have been given to you. Simulator output which shows the stimuli relevant memory location values showing validation based on test plan. So make copies of what you saw in your simulation, right? So maybe do something like I already cleared out my windows, but put a stimulus window in one spot, put your watch variables in another spot. And step your simulation, take some screenshots. Okay, so most systems you can do screenshots. Print screen still works on most systems, so I can make a screenshot like that. And crop it to whatever the appropriate section is. And then if I've got my report and I want to put this in, right, I can just drag that in and, right, and I'm probably back to my normal font. Right. So plan on spending some time detailing your report, figuring out how you want it to look, and figuring out some tools to let you do things like put screenshots in, or change to a fixed space font, and so on and so forth. All right. Report as a whole, again, cover sheet, lessons learned, new experiment at the end. That's your lab report. So that's due a week from today at the start of class. Okay, all the assignments are due at 12 p.m. That's 12 noon, not 12 midnight. Okay, so don't make that mistake. And probably no homework questions we can really get into yet. So so Thursday we'll jump in full bore on looking at assembly language, and then we'll post homework questions for that. All right, I will keep the Zoom room open. Go ahead and start working on your labs. I'm going to stop recording so you can catch me on chat. You can send me a private chat if you want, and we can screen share and so on and so forth. All right, so go ahead, hop into the labs, and I'll be here for the next 2 hours if you need any help.